Welcome, curious minds, to the deep dive. Today, we're taking a shortcut, a direct route, really, to getting smart about an industrial process that's, well, it's foundational, submerged arc welding, or SAW.
That's right.
We've got our sources lined up, and the mission today is to pull out the key stuff, the really fascinating bits, without getting lost in the weeds.
Exactly. If you've ever wondered how, massive ships or those huge pressure vessels get put together with such strength and precision, SAW is often the unsung hero behind it all. We'll unpack how it works, what makes it unique, and why it's the go-to for some of the biggest welding jobs out there.
Okay, let's dive right in then. We're pulling back the curtain on SAW, looking at everything from how that arc works, totally hidden under powder,
Right,
to how tiny tweaks can make a massive difference in the final weld. Get ready for some real aha moments, I think.
the hidden arc understanding submerged arc welding.
So submerged arc welding, the name itself, it paints a picture, something hidden. What exactly is going on under that powder layer? It seems kind of backwards for welding.
It does sound a bit strange at first, but the ingenuity is fascinating. So picture this. You've got a continuous bare wire, that's your electrode, feeding down towards the metal parts you're joining.
Okay.
An electric arc strikes between the tip of that wire and the base metal. That arc generates intense heat, melting both the wire and the metal.
Standard enough so far?
But here's the kicker, the key part.
No.
The entire show, the arc itself, the end of the melting electrode, the molten pool of metal, it's all completely buried, submerged under this thick blanket of granular, powdery stuff called flux.
Right, the flux. So it's not just there for decoration. Is it doing something important?
Absolutely. Far from decoration.
Yeah.
It's really the heart of the process. When that intense arc heat hits the flux right near it, those lower layers melt and react. They turn into molten slag and also release gases.
Okay.
And this combination creates this protective bubble, this shield, right around the molten weld pool. It completely seals it off from the air, from oxygen, nitrogen, contaminants.
Which is obviously critical for a good weld.
Critical. It prevents defects, ensures high strength, and there are other benefits too. Because it's all contained, there's basically no spatter. And importantly, no bright arc flash. So no harmful UV or infrared radiation for the operator, which is a huge safety plus compared to other methods.
That is a big deal.
Definitely. Plus, the unmelted flux on top, you just vacuum it up and reuse it. Makes it pretty efficient.
Now, something that really jumped out at me was the power levels. The sources mentioned really high currents. How high are we talking?
Yeah, SAW is a powerhouse. It thrives on high current. We're often talking up to, say, 1,000 amps, sometimes even more, depending on the setup.
1,000 amps, that's a lot.
It is, and that's what gives you that deep penetration into the metal and really high deposition rates. You can lay down a lot of weld metal fast. Deep penetration is really a signature of SAW.
So that's usually with DC current.
Often, yes. DC positive gives you that deep penetration. But for some applications like cladding, putting a protective layer on top of another metal, you might actually use DC negative. That reduces the penetration so you don't dilute the cladding layer too much with the base metal.
Okay.
And when you get to really high currents, or if you're using multiple wires at once, AC, alternating current, becomes common. It helps prevent something called arc blow.
Arc blow.
Yeah, it's basically a magnetic effect that can push the arc off course, make it unstable. AC helps counteract that. Sometimes you'll even see systems using both maybe DC on the leading wire for penetration and AC on the trailing wire.
Fascinating. So with all this power and the flux, where does this get used? What kind of big projects rely on SAW?
Good question. The main limitation, because of the loose flux and gravity, is position. You're mostly restricted to flat welds or horizontal fillets. You can't really weld vertically up or overhead easily.
Right, the flux would just fall off.
Exactly. But within those limits, it's huge. Shipbuilding, absolutely massive structures. Pressure vessels for refineries or chemical plants. Large diameter pipes for pipelines, crossing continents. Even things like railway carriages.
So long, heavy-duty welds.
Precisely. Anywhere you need long, strong, consistent welds, especially on thicker materials, say 5 millimeter thick and upwards, and it works on a range of metals. Common carbon steels, low alloy steels, stainless steels, even some nickel alloys, and like we touched on for cladding too, adding wear or corrosion resistance.
One thing I wondered, if the arc is hidden, how do you make sure you're welding exactly where you need to? How do you guide it?
That's a really sharp observation. It is a challenge, welding blind essentially. You can't just eyeball the arc following the joint line.
So how do they do it?
often with a mechanical guide. A small guide wheel, or sometimes a probe, is positioned just ahead of the welding torch and the flux hopper. This wheel actually runs in the prepared joint groove.
Ah, like a little train on a track.
Kind of, yeah. It physically steers the whole welding head assembly, keeping it precisely on the intended path. So even though the operator can't see the arc, the machine follows the track. It's a clever mix of automation and simple mechanics.
The mighty powder, all about fluxes.
Okay, we keep coming back to this flux, this magic powder. What actually is it? And you mentioned different types, fused and agglomerated.
Right. The flux is absolutely central. It's not just one thing. It's a carefully formulated mix of granular mineral compounds. Think of it like a recipe designed to do specific jobs during welding. And yes, the two main manufacturing methods give us fused fluxes and agglomerated fluxes.
Okay, let's start with fused. How are they made? What are they good at?
Fused fluxes, well, they start by mixing all the raw mineral ingredients dry. Then they melt the whole batch together in a big electric furnace, super high temperatures.
Okay, melted completely.
Completely. Then they rapidly cool that molten mix, often by pouring it into water or onto ice. That shatters it into glassy granules. These are then crushed and screened to get a consistent particle size.
Sounds pretty robust.
They are. The big plus is chemical homogeneity. Because everything was melted together, each grain is pretty much the same. This leads to a very stable arc, consistent results, usually a nice weld appearance. They're also less hygroscopic.
Meaning they don't absorb moisture easily.
Exactly, which makes them easier to store and handle. And recycling the unused flux works well, it doesn't change much. The downside, the high melting temperature limits what you can put in. Some beneficial additives, like certain carbonates or extra deoxidizers and alloys, just don't survive the process or don't mix well. Physically, they tend to look glassy, maybe black or dark hard particles.
All right, so if fused fluxes are melted, what's the deal with agglomerated fluxes?
Agglomerated fluxes use a different approach. Instead of melting, they mix the dry powder ingredients with a liquid binder, often potassium or sodium silicate, basically a sticky liquid glass.
It's like making little clumps.
Pretty much. The wet mix is pelletized, then dried at much lower temperatures compared to fusing, then crushed and screened like the fused type.
Okay, so lower temperature process. What's the advantage there?
Flexibility is the key advantage. Because you're not melting everything in extreme heat, you can easily add things like deoxidizers, which clean the weld metal, or specific alloying elements, maybe chromium or molybdenum, directly into the flux mixture.
Ah, so you can tailor the weld chemistry more easily.
Precisely. You can fine-tune the final weld metal properties by choosing the right agglomerated flux. They also tend to allow a slightly thicker flux layer during welding. You can often tell them apart by their duller look, irregular shape, maybe even different colors depending on the formulation.
But there must be drawbacks too.
There are. They are generally more hygroscopic. They suck up moisture from the air much more readily. So storage and handling are critical. Baking them to re-dry can be tricky because the binder itself contains some chemically bound water.
And moisture is bad for the weld, right?
Very bad. Can lead to porosity, those little gas bubbles, or even hydrogen cracking. Another potential issue is segregation. Because it's a mix of particles held by a binder, rough handling could cause the finer bits, maybe richer in alloys, to separate out. So consistency can be slightly more challenging than with fused types.
Fascinating trade-offs. So fused versus agglomerated. But stepping back, what are the fundamental jobs any soft flux has to do?
Good question. Regardless of type, every soft flux has several core functions. Number 1, shield the weld. Keep the air away from the molten metal.
Okay.
Number 2, clean the weld pool. React with impurities, float them to the surface as slag. Number 3, potentially modify the weld chemistry, adding alloys or compensating for losses.
Right, tailoring the property.
Exactly. They also help control the cooling rate by insulating the weld, and they heavily influence the final shape and appearance of the weld bead. And the crucial takeaway for any flux: keep it warm, keep it dry. Moisture is the absolute enemy. Always follow the manufacturer's instructions for storage and drying.
The control panel mastering process variables.
It definitely sounds like SAW is powerful, but also needs careful handling, like a delicate dance of variables. What are the main knobs operators are turning, and how do those adjustments change the final weld?
You're spot on. It is a dance.
Yeah.
While it can be highly automated, controlling the key process variables is crucial for getting the right weld quality, appearance, and mechanical properties. There are several critical ones.
Let's start with the obvious one: welding current, the power dial. What happens when you crank that up or down?
Okay, current. Increasing the current directly increases the heat input. This has two main things. It increases the depths the arc penetrates into the base metal, and it increases the rate at which the electrode wire melts, the deposition rate.
So more current equals deeper weld, more metal filled in.
Generally, yes, but there's always a limit. If you push the current too high, you risk burning right through the material, especially if it's thinner. Or you can get undercut little grooves melted into the base plate along the weld edges. It can also create a really deep, narrow bead that might be prone to cracking as it cools.
And too low.
Too low, and the arc can become unstable, fluttery. You won't get enough penetration, which is often the whole point of using a SIW. And you might get lack of fusion. The weld metal just doesn't bond properly to the sides of the joint. You can definitely see distinct profiles if you compare, say, a weld at 350 amps versus one at 650 amps.
Okay, makes sense. What about arc voltage? How critical is that?
Voltage is another major player. It primarily controls the length of the arc under the flux. Increasing the voltage makes the arc longer. Its main effect is on the shape, the profile, of the weld bead.
How so?
Higher voltage tends to produce a flatter, wider weld bead. It also increases how much flux gets melted. This can actually be helpful sometimes, maybe bridging a slightly wider gap between parts or helping to float out impurities like rust or scale. It also increases the pickup of alloying elements from the flux if you're using an alloyed flux.
So wider, flatter. What's the downside of too much voltage?
Too high. And that wide, flat bead can become prone to solidification cracking, especially down the center line. Slag removal can also become much harder, particularly in narrow grooves. You might get a concave flea weld shape, which isn't ideal structurally, and you risk over-alloying the weld metal from the flux, changing its properties perhaps undesirably.
And if the voltage is too low?
Too low gives you a stiffer, shorter arc. This can actually improve penetration in really deep, narrow joints and help fight arc blow. But go excessively low, and you end up with a tall, narrow, ropey-looking bead. And again, slag removal can be a real pain, like current. Changing voltage shows clear differences. A weld at 25 volts looks very different from one at 45 volts.
Right. Travel speed seems simple in just how fast you move along the joint. Any hidden complexities there?
It seems simple, but it interacts with everything else. If you increase travel speed, holding current and voltage constant, you're putting less heat into each unit length of the weld.
Because you're moving faster.
Exactly. So you deposit less filler metal per inch or per millimeter. The bead gets smaller, narrower, and crucially, penetration decreases. So faster ski generally means less heat input, smaller bead, shallower penetration. Again, very noticeable if you compare different speeds.
Okay. And electrode size. Does using a thicker or thinner wire change things significantly?
Absolutely. Electrode size impacts the current density for a given amperage. A smaller diameter wire at, say, 500 amps has a much higher current density than a larger wire at the same 500 amps.
And higher current density means?
It usually means a stiffer, more focused, more penetrating arc. So smaller wires can give deeper penetration for a given current. However, a larger diameter wire can carry more total current before overheating. So if you want the absolute highest deposition rate possible, you'd likely use a larger wire and crank up the current accordingly. Switching between different standard sizes, like 3.2 millimeter versus 5 millimeters, makes a big difference in the weld profile and how much metal you can put down per minute.
Interesting. Is there anything else? Any other key variables?
One more that's quite important is electrode extension, or stickout. This is the length of the electrode wire extending out from the electrical contact tip before it reaches the arc.
Okay, how does that matter?
Because the wire has electrical resistance. As that high welding current flows through that extended length of wire, the wire itself heats up due to resistance. It's called I²R heating.
So it preheats the wire before it even hits the arc?
Exactly. And this preheating effect can significantly increase the wire's melting rate, sometimes by 25%, maybe even 50% or more with a long extension.
Wow. So longer extension, faster melting.
Yes. But there's a trade-off. That extra energy going into melting the wire means slightly less energy is available in the arc for penetrating the base metal. So longer extensions usually lead to slightly decreased penetration and maybe a slightly wider, flatter bead, even though the melt-off rate is higher. It's another parameter operators use to fine-tune the process.
The essentials equipment and care.
This definitely sounds like it needs some serious machinery, highly mechanized. What's the typical equipment setup for SAW? And how crucial is keeping the materials themselves, the wire and flux, in perfect condition?
Yeah, the equipment reflects the industrial scale where SAW shines. You've got the heart of it, the power source, usually a heavy-duty transformer rectifier capable of delivering those high AC or DC currents reliably.
Right.
Then there are control panels to set the current, voltage, speed, etc. The welding head itself holds the wire feeder mechanism and the contact tip. This head is usually mounted on some kind of travel system.
Like a carriage.
Exactly. It could be a motorized carriage, sometimes called a tractor unit, that runs directly on the workpiece or on a temporary track for long, straight welds, like on pipes or beams. For bigger, more complex parts in a workshop, you often see column and boom manipulators.
Like a big robotic arm.
Sort of, yeah. A vertical column with a horizontal boom that can extend, retract, raise, and lower, carrying the welding head. Provides a lot of reach and flexibility. And of course, you need the flux delivery system, typically a hopper above the weld head feeding flux down through a tube to cover the arc and the wire feed system, often handling large spools or drums of wire.
Okay, so robust gear. Now, about those materials.
Yeah.
You've stressed keeping flux dry. What about the wire? How important is keeping everything clean?
It's absolutely paramount. Contamination is the enemy of a good weld, especially a high-quality structural weld made with saw. Any oil, grease, rust, dirt, even heavy dust on the wire or mixed into the flux can cause serious problems.
Like what kind of problems?
Well, oil and grease can introduce excess carbon into the weld, potentially making it brittle. Rust is particularly bad because it contains moisture and oxides. Moisture, whether from rust or damp flux, breaks down in the arc and releases hydrogen.
And hydrogen is bad news in steel welds, right?
Very bad news. It can lead to hydrogen-induced cracking, sometimes called cold cracking or delayed cracking, which can cause catastrophic failures. So wires need to be kept clean, stored properly. Often they have a thin copper coating, partly for corrosion resistance, but also for good electrical contact. Flux needs to be stored dry, often in heated holding ovens, and dried according to the manufacturer's specs before use, especially the agglomerated types. You just can't afford contamination when you're relying on these welds for structural integrity. Outro.
Wow. Okay, we have really gone deep into submerged arc welding today. From understanding that completely hidden arc and the vital role of that powdered flux.
Doing multiple jobs at once.
Right. Shielding, cleaning, shaping, and then navigating that intricate dance of process variables, current, voltage, speed, stickout that operators have to master. It's clear SWIP is this blend of brute power and real precision.
It really is. And what strikes me is how those seemingly small adjustments, a few volts here, a bit faster travel speed there, or just ensuring your flux is perfectly dry, how they have such profound effects on the final quality and strength of these enormous structures. Bridges, ships, pipelines.
Things we rely on every day.
Exactly. It underscores that blend of applied science and skilled craftsmanship that goes into modern fabrication. Understanding these details isn't just academic, it's fundamental to safety and reliability.
So what does this all mean for you listening? Well, next time you see a massive container ship or read about a new power plant being built, maybe think about the welds holding it together. There's a good chance saw was involved, working away silently, powerfully beneath that layer of flux.
A hidden giant of industry.
Totally. And it makes you wonder, doesn't it? What other incredibly complex, precisely controlled processes are underpinning the world around us, hidden just out of sight? Something to think about. Until our next deep dive.